last lecture we talked about confidence interval for the population mean when your sample is continuous. Now we talk about a confidence interval for population proportion. So suppose that we have a binomial random variable with parameter p, and we know that this x divided by n, x over n, denoted by p hat, is an unbiased estimator of p. And we can easily prove that. And we can also get the variance of p hat. Variance of p hat, so here I list steps for variance of p hat, and it will be equal to p times 1 minus p divided by n. And if you take a square root of it, then we call this a standard error of p hat. And by central limit theorem, we have this equation. So this is because the expected value of p hat is p. So p hat minus p is called centralization. It is like we centered this p hat, and then divide by the corresponding standard error, we call it standardization. So by central limit theorem, when n is sufficiently large, so this quantity will follow a normal 0, 0, 1. So this follows normal 0, 1. And by the property of standard normal distribution, we have the following equation. Then by rearrangement of this, we should get this inequality as p is greater than or lower bound and p is less than the upper bound. However, since this form is a little bit complicated, so we use p hat to estimate the denominator. So that is to say, in order to get a confidence interval for p in an easier way, so we plug in p hat, okay, in the denominator. And so that's where this comes from. Then by rearranging this quantity, so we have this following result. So that is to say, the lower bound of the confidence interval for p is p hat minus this quantity. Okay, margin of error, we call this margin of error. And the upper bound is just p hat plus this margin of error. And to utilize this calculation of confidence interval, we should so there are two conditions you should satisfy. The first is n times p hat should be greater than 0, which is, we can call it the observed success, right? This is the observed successes. Then n times 1 minus p hat, we can call it observed failures. That is to say, if we want to utilize this confidence interval, we have two conditions must be satisfied. The first one is the observed successes must be greater than 10, and the observed failures must also be greater than 10. And now let's see an example. So since in this example our p hat is 5 over 12, then n p hat will be equal to 25, and n 1 minus p hat is equal to 35. So both of them are greater than 10. So we can utilize the confidence interval calculation for the population proportion. And by plugging in the above numbers, then we get a confidence interval. We get a confidence interval like this. And so why do we need, how do we find this number? So this number is a z quantity. Okay, so this number, is here. It is a quantity that makes the area to the right of it equal to 2.5%. And now, instead of the 60 balls and 25 red balls. Now think about how about we have 600 balls, and among which 250 are red. So that is our p hat is still the same. However, the confidence interval changed because our n here changed to 600, right? So that will result in a narrower confidence interval, because you can see the lower bound becomes larger and the upper bound becomes smaller. Now, very similar to confidence intervals, we talk about confidence bounds. So confidence intervals have both lower bound and upper bound. However, confidence bound has only either upper bound or lower bound. So when we are only interested in a lower bound or an upper bound for mu with some confidence, then we should use the confidence bound. And by central limit theorem, when n is sufficiently large, this quantity x bar minus mu divided by s divided by square root of n, this approximately follow normal 0, 1. And because of this, we have this probability relation. We have this probability relation, and by rearranging the inequality, we can find a lower bound for mu. Then a lower bound for mu, then plug in the x bar and s, where s is the sample standard deviation. So here is the sample mean, and here's the sample standard deviation. So we get a lower bound for mu. And similarly, we can get an upper bound for mu. Now, if a sample of 48 observations has mean value 17.7 and the sample standard deviation is 3.28, then we know, so this sentence already tells us lots of information. That is to say, n is equal to 48, x bar is equal to 17.17, and s is equal to 3.28. Then by plugging in the numbers, then we get a lower confidence bound for it. Now, in order to get a 95% lower bound, then we need to find z sub 0.5. So what's that number? So this number is the number such that the area to the right of this number is 0.05 under a normal z. So we can call it normal z. So this is the density for the standard normal distribution. And now we talk about intervals based on a normal population distribution. So before, we know that even if the population is not normal, we can still use central limit theorem to derive a confidence interval, right? However, that confidence interval will be approximate. Now, let x1 to xn be a sample from normal distribution. However, this time sigma is we know that if sigma is known, then we have seen that a confidence interval for mu with confidence level 1 minus alpha will be equal to the following, right? Now, what if sigma is unknown? When sigma is unknown, we can use sample standard deviation to replace the sigma, right? And we call this quantity t, and we find that, and we the distribution of this quantity, we call it t distribution. And the t distribution is characterized by degrees of freedom. And a t quantity calculated in this way has n minus 1 degrees of freedom, where n is equal to the sample size. So let's observe some properties of T distributions. Since T is characterized by degrees of freedom, so at different degrees of freedoms, the T distribution will look different. As you can see from the plot, when your degrees of freedom is very, very large, when your degrees of freedom approximates infinity, then your T density will be tall. And when your degree of freedom is very small, say you only have 1 degree of freedom, then your T density is kind of shorter, so which means that your density will be spread out more. So 4 properties of T distribution. So the first one is T curve is always bell-shaped and centered at 0. Right? This is not the same as normal distribution, because normal distribution may not center at 0, right? Because normal distribution center at mu, where mu can be any real number from negative infinity to infinity. So each T distribution is more spread out than the standard normal curve. That is to say, T distribution has more variance than standard normal curve. So standard normal curve means the curve for normal 0, 1. And as the degree of freedom increases, the spread of the T curve decreases. That is to say, if you increase the degree of freedom of T distribution, then the variance will be greater. The variance will be smaller. And as the degrees of freedom goes to infinity, then this T distribution will be very, very similar, almost equal to the standard normal distribution. And very similar to standard normal distribution. So if this is T distribution, then with degree of freedom nu, then we call, and if this point is a point such that the area to the right is alpha under the curve, then we call this quantity T alpha nu. Now, since we already know that this quantity follows a T distribution, then we can utilize the property of T distribution. So since this quantity follows T distribution with n-1 degrees of freedom, then the probability that this quantity falls within these 2 points are just 1 minus alpha, because the right tail has alpha over 2 and the left tail has alpha over 2 as well. So the probability that this random variable stand in between is 1 minus alpha. And if we rearrange it, we get lower bound for mu and upper bound for mu as well. So this, we call it a confidence interval for mu, and this is a exact confidence interval. There's no approximation here. And in very similar argument, we can find confidence bound, either upper bound or lower bound for mu using T distribution. And here is a summary. So example, if a random sample has size 10 and is generated from a normal distribution with unknown mu and sigma. So this sentence contains lots of information as well. So it already tells us that n is equal to 10, right? And because we know that it's from normal, right? And sigma is unknown, then this tells us that we should utilize T distribution. Then by plugging in the numbers, by plugging in the numerical values, then we get the formula for getting upper bound and lower bound of confidence interval. And the key point is that we should find this number, right? We should find this number. So this number is, you can find it from your calculator. So what is this number? This number is just to find a T9 distribution, and it's always centered at 0, and this number is the number such that the area to the right of this number is 0.025, and we call this number T.025, 9. And we talked so much about confidence interval, and confidence interval is an interval for mu. Now we talk about prediction interval. Prediction interval is an interval for xn plus 1, where xn plus 1 is a future observation that we would like to predict. Now this is a fact. Okay, this is a fact. And so those are two facts you should know, and you don't need to know why, but you don't need to know why this hold, but these are two facts that is already given to you. So which means that this quantity follows a standard normal distribution, while this quantity follows a t distribution with n-1 degree of freedom. And by if sigma is known, then we use the z, right? Because this quantity follows the z distribution, which is standard normal, then the probability that this quantity falls within these two numbers will just be 1 minus alpha. And by rearranging this quantity, then we have the following inequality for xn plus 1. And this is a lower bound for xn plus 1, and this is the upper bound for n plus 1. And so let's observe what's the difference between prediction interval and confidence interval. So recall, what is a confidence interval for mu when your sigma is known? It is this, right? So confidence interval for mu. Right, so these two are very similar. The only difference is in this one. So you can see the prediction interval is wider than the confidence interval due to the existence of 1. And how about when the sigma is unknown? So when the sigma is unknown, we utilize the t density, right? Because we have already known that this quantity follows a t distribution, right? And we just plug in the we just utilize that formula for confidence interval. So another example, now suppose we have x bar equal to 905.5, and here sigma is unknown, right? Sigma is unknown. So we only know the 197.12, which is the sample standard deviation. So we plug in to the confidence interval when we plug into to the formula, okay, that calculates the confidence interval when the sigma is unknown. So that gives us this quantity. And again, what is T.025? So this quantity, so if this is a T9 distribution, right, so it is centered at 0, then this quantity is a quantity such that the area to the right of this quantity is equal to 0.025. We've talked confidence interval for mu, for p, right? Now we talk about confidence interval for variance and standard deviation of normal population. Here is another fact. Here's another fact. So suppose S is our sample variance, which is defined to be sum of square divided by sum of square over n minus 1, then this distribution has a chi-square distribution with new degree of freedom. If you have already forgotten what is a chi-square distribution, you should refer to the previous notes. And a chi-square distribution is not symmetric, and it only take values from 0 to infinity. So a typical chi-square distribution looks like this, and chi-square distribution is also characterized by degree of freedom. So if this degree of freedom is new, right? So what is chi-square? So what is chi-square? So what is this quantity? So this quantity is the quantity such that the area to the right is alpha, and we denote it by chi-square alpha nu. So this hold, right? And what is this quantity? So this quantity is a quantity such that the area to the right is 1 minus alpha. That is to say, the area to the left of this quantity is alpha. And because of the property, we know that this chi-square random variable, the probability that this chi-square random variable stand between these two numbers are 1 minus alpha. And by rearranging the inequality, then we get a lower bound and upper bound for sigma. So these two quantities are very important. So we should calculate that if we want to know the confidence intervals for sigma square. Now, and it's obvious that this S square can be obtained from our data, which is the sample variance. And because sigma square, okay, because this is a confidence interval for sigma square. Now, if we take a square root of the lower bound and upper bound, so this is a confidence interval for sigma.